Coming to DARPA is like grabbing the nose cone of a rocket and holding on for dear life.
DARPA is a place where if you don't invent the internet, you only get a B.
A DARPA program manager quite literally invents tomorrow.
Coming to work every day and being humbled by that.
DARPA is not one person or one place. It's a collection of people that are excited about moving technology forward.
For more than 60 years, DARPA, the Defense Advanced Research Projects Agency, has held to a singular and enduring mission to make pivotal investments in breakthrough technologies for national security. Working with innovators inside and outside of government, DARPA has repeatedly delivered on that mission, transforming revolutionary concepts and even seeming impossibilities into practical capabilities. Welcome to Voices from DARPA, a window onto DARPA's programs, partners, and performers. My name is Stacy Wurzba, and I'll be your DARPA host today. According to a 2021 report jointly issued by the WHO, the World Food Program, and others, quote, "The high cost of healthy diets and persistently high levels of poverty and income inequality continue to keep healthy diets out of reach for around 3 billion people in every region of the world," unquote. In this episode, we're discussing two programs aimed at addressing issues in food security. First, we will hear from Dr. Molly John, Program Manager for the Cornucopia Program, which seeks to enable food production on demand and on-site. Next, we'll speak with Dr. Blake Bechstein, who manages the Resource Program, and Dr. Stephen Techman from Michigan Technological University, who serves as a program performer on their unique approaches to this daunting problem. That program aims to turn military waste, including plastics, into oils, lubricants, and food. Dr. Molly John.
Food security is when all people at all times have physical and economic access to safe, nutritious, sufficient food that meets their dietary needs and food preferences for a healthy and active life. Current events make it very clear that the global food system is complex, it's deeply interconnected. It has been, over the last decades, optimized for peacetime, relatively stable environmental conditions, and globalized trading regimes. And we have a series of large-scale dynamics that place significant portions of the globe at risk for serious food instability. So both within the U.S. and around the world, stability of food supply is a crucial foundation for civil stability and security. My dream is to take food off the table in terms of a means to control populations or as a source of civil instability or human beings falling short of their ideal potential with regard to dietary health.
Dr. Blake Bechstein.
My interest actually developed in food security from an early age. I come from an agricultural background, and so I understood well the food supply, the logistics, and some of the difficulties that come with production. Global food security is something that affects every nation on Earth, and it's something that runs through the economic status globally. And so when we think about making sure that we're ahead of those problems, as far ahead as possible, we want to have a nimble system where we can solve whatever pops up. New insects show up in different countries and affect certain markets. A new pathogen emerges in a different part of the country. We also live in a much smaller world. So any of the problems that we see emerging on the other side of the globe ultimately move around the Earth maybe faster than they used to because of the way that we have this globalized society. There are new problems that pop up almost every day. And the further ahead of those problems we can get, the more secure our food supply is going to be. And this isn't something that just affects the U.S. population. It doesn't just affect the military. It affects all people. I developed a hypothesis, I suppose, that, if we can get as far left of conflict as possible, if we can secure food, then maybe conflict gets reduced.
To solve monumental issues, such as those associated with global food security, You need big ideas and lots of them.
I wanted to be a ballet dancer until I was misdiagnosed with terminal cancer at age 13. And at that point, I went through all of those things you go through when you face your mortality, and then it was a mistake. And at that point, I got really interested in how systems heal and in what health was, but not necessarily personal health. And at the time, there was a kind of growing recognition of the ways in which humans were poisoning our environment. And so really my interest in agriculture and food systems came from an interest in harmonizing humanity's needs with the limits of the planet. I became interested in issues that relate to food, its production, its integrity, its biology, and the consequences of the choices we've made as we develop our food systems really very early. I started out as a little kid with a vegetable garden and became ultimately a plant scientist, plant geneticist, plant breeder.
When I was in college, I was a biology major, and I thought that I was going to go to medical school and go that route. And I took a class in entomology. And the class in entomology really brought to light, opportunities that we have scientifically to study something that's incredibly important. And insects are a large part of the agricultural production cycle. And so focusing on insect science and food production really became a core interest of mine as I went through college. And then I found out that you could get assistantships to get a master's degree and even move on to get a PhD. And that really developed my pathway into this area. And one of the things that I noticed as I was going through my education was that there are always problems to solve.
I had been very involved, both domestically and internationally, focusing on building out the framing of risk in food systems and the economic and physical risks that go along with that. But when the pandemic hit, I received an invitation from our deputy director to prepare a seminar for DARPA. I used that opportunity to do something I had never had a chance to do before, and that was to move beyond describing the problem to think about solutions. And the solution I came up with was to, in essence, completely redesign the way we provision ourselves with regard to food. So what would it look like if we flipped the way we source our food on its head and devised ways to produce food anywhere human beings can exist with the energy that those human beings have on hand at that time? So in order to do that, we have to look to microorganisms which grow much more quickly. In fact, NASA decades ago identified a bacterium that can live off literally the hydrogen gas from splitting water. So all you need to grow that bacterium is water, air, and electricity. So riffing off of that science, Cornucopia modeled out what it would take to create systems that are deployable, that is, systems that can be run where humans are located. So food is produced at the point of consumption, and the food is microbial origin. So Cornucopia, in a nutshell, is microbial origin foodstuffs produced at point of consumption within the energy envelope, as well as size, weight, and power, that would be necessary to make those systems deployable. What gets me up in the morning is the idea that we are not so far away from offering an alternative to today's systems that is tractable, it's commercially viable, it's very sensible. There's no reason, theoretical or practical, that we couldn't see this happen.
In mythology, the cornucopia was the magical horn of plenty, providing an unending supply of nourishment from nothingness. The DARPA Cornucopia program, while not magic, could certainly appear to be with its aim to create food from essentially invisible sources: microbes, air, water, and electricity. Shifting perspective, DARPA's resource program also looks to tackle the problem of food security, but from more tangible means.
In the resource program, we were really looking at a problem that hits on two sides. So on one side, we have a waste material issue. We were really looking at plastic. It's everywhere, every day. And the U.S. military actually uses a huge amount of plastic, and it becomes a burden just getting rid of it. And what's interesting about plastic is that it's made of molecules that are energy dense, but biology can't get to them. And so because biology can't get to them, it doesn't break down very readily. So what we want to do is break it down into consumable pieces for biology. So if we just accomplish that, it's something that could go back into the environment as a safe waste material. But what we're thinking is if we can get down to this consumable piece that's energy dense, we can upcycle it into proteins, fats, and carbohydrates in a very specific way. And we can produce food products that can further be developed beyond that. We've gone further with that idea, and we actually have a small business effort out right now to take this material that's going to be energy dense and dynamically made of proteins, fats, and carbohydrates and turn that into an actual palatable food product. And that's maybe going to be through 3D printing. And we have some other pretty cool ideas. So stay tuned. So when we were doing research, trying to figure out, a good reason to do this and why it's military relevant, we were actually looking at some of the materials that are waste from military operations. And one particular example really struck a chord with us, and that was that MREs, meals ready to eat, these are the packaged foods that soldiers will take out into the field when they're gone for several days.
I happen to have an MRE, or meal ready to eat, here with me, thanks to our friend in the Air Force.
The packaging actually has more energy contained in the plastic material than the number of calories that's in the food. And so we were looking at that, doing some calculations back of the envelope, thinking, we just realized that we could harvest that and get more energy out of the packaging of an MRE than what's in the food. It's amazing.
So how much energy are we actually talking about here? Part of the process of creating any program at DARPA is establishing milestones. What metrics would need to be met in order to achieve success?
We used two use cases. One was a forward operating squad. So this is a small group, generally modeled after a forward squad of males in peak physical condition. So this puts the maximum stress on the system in terms of its nutritional output. And that system has to run for 45 days and produce a nutritionally complete foodstuff. The other use case we developed and did all our calculations for was a humanitarian mission where the population was a group of civilians, both sexes, all ages, maintained at the subsistence level, basically at survival level, for 21 days. So we're hoping that the program will create solutions that are tailorable for the human needs at that site at that time, from a nutritionally complete output that will sustain a warfighter in peak condition to capabilities that will address humanitarian situations.
In the resource program, we actually funded 4 large groups that are taking the process all the way from waste breakdown to development into, in 3 of the groups, a food product. And then we also have a concept turning that material into lubrications and oils for different mechanical purposes. But the teams are working on 2 different formats. One of them is working on a larger format that might fit in, a Connex box, semi-size structure, and would be able to provide, waste reduction and food production for 100 people over a 30-day period, kind of in a continual system. The other is something smaller that would fit, in the back of a pickup, could be carried by a small unit into the field and could provide food material for 10 to 12 soldiers over, a week or 2 period. And that's what we're driving towards.
Dr. Stephen Techman, an associate professor at MTU in the Upper Peninsula of Michigan, describes his work on the DARPA resource program.
I am part of a team of scientists and engineers that are trying to use bacterial communities to convert plastic wastes into valuable products, in particular food. And what we have been trying to do is to leverage the power of bacteria to convert the wastes into something edible. The problem with plastics is, though, that they are incredibly difficult to break down. And while there are bacteria that can break them down, bacteria on their own need a little help. And so what we've been doing is working with some chemical engineers that have methods to take plastics and break them into something that's more biodegradable. And in doing this, we can take plastics, use chemicals and heat to break them down, and then feed them to these communities of bacteria that will chew on that broken down plastic and turn it into microbial cells. And so what we are hoping to do is recover this biomass and use that as a food source. Where we are in that project is we've been able to show that we can get this to work on the small scale. We can feed in a couple different plastic types on the front end of our system and recover small amounts of bacterial cells on the other end. And we're trying to scale that up and integrate this. Ultimately, what we want to do is have a system that could be deployed in a low resource environment, in austere environments, and be able to perform this process efficiently with limited user input.
Now seems like a good time to point out that DARPA doesn't do research just for the sake of doing research. To truly be successful, the work has to transition. With foodstuffs like those created in Resource and Cornucopia, it's essential that the end product is healthy, accessible, and, most importantly, edible.
I think one of the biggest challenges for us is going to be ensuring that the food product we're producing is fully nutritious and is non-toxic. And these are things that we have to be very cognizant of as we're developing this food product that we hope to be able to feed to people.
So a lot of times people get confused with microplastics and what's happening there. That's not actually molecular deconstructed materials. That's physically deconstructed. So you get these small particles that become problematic. In our system, we're looking at the molecules and actually looking at like the carbon atoms within that and looking at the breakdown process at that like super micro level. And so what ends up happening, if you think about when you breathe in oxygen and you breathe out carbon dioxide. That oxygen is the same, right? It's just cycling. And so you can think of Resource as really just a different way to cycle that carbon through the system and utilize it and rebuild it in a different way.
So palatability is a central part of Cornucopia. One of the really exciting chunks of science that we are mobilizing into Cornucopia is remarkable work that's been done around the chemical properties that result in flavor. So part of Cornucopia requires our scientists to learn how to flavor microorganisms that are suitable for consumption as human food. We have looked at a broad array of options for expressing those flavors literally as part of the microorganism's growth. So there are other approaches to flavoring from the outside, but I'm expecting that a central way forward is simply to add those flavors to the microorganisms so they come out flavored in ways that make the food palatable. We did sort of bake in to the metrics of the program the need to be tailorable, because a really important part of palatability is not only desirable flavors and smells, but also a variable diet.
Recent advances in the fields of biology and chemistry are finally making programs like Cornucopia and Resource possible.
There are lots and lots of exciting things that are happening in chemistry. And there are lots and lots of exciting things that are happening in relevant biology with the advent of very, very low-cost genomic sequencing, the discovery of extremophile bacteria all over the world with amazing metabolisms. Really, there is a lot of frontier left in microorganisms with the addition of genome editing and synthetic biology, the ability to move these metabolisms around in organisms that are amenable to this kind of culture. It's a very exciting kind of convergence of the biology, the chemistry, and then the engineering that it would take to run these systems off relatively low amounts of energy.
there's a lot of exciting things about this idea of using microbial cells as food because it addresses some of the challenges that we're facing with traditional agriculture. The world's population is growing. We're going to need to feed this growing population. And because of climate change, we're losing arable land. And so traditional agricultural practices alone are going to be a tool that we can use, but we have to think outside the box. And that's what I think is exciting about some of these programs. We're creating technologies that can be used in these specific cases, like we're developing for these expeditionary forces, but there is potential to scale that. And if we, in scaling it, this could be another tool that we could use to address food insecurity.
Once we develop sort of the fundamental piece of this and show a proof of concept, we lower the bar for the next step of research. And so that could go in a lot of different directions. And one of them would definitely be within the civilian sector.
It's going to take a lot of people. It's going to take a lot of solutions. And if we're just one of those, then I think it's pretty impactful.
DARPA explicitly reaches for transformational change instead of incremental advances, but it does not achieve this alone. The agency works with diverse collaborators in academia, industry, and government to ensure that our vision is realized for the betterment of the warfighter and the greater community.
I've come to DARPA, among other things, to begin to address some of the concerns and issues that I think reside in that intersection between the stability and function of food systems and national security, U.S. economic and U.S. national and global security.
But then at DARPA, we're always thinking, how do we not just solve the problem, but how do we solve the next problem before it gets here? So, that gave us the opportunity to look at waste reduction and also food production, because food security is an incredibly important issue.
So I really enjoy working with DARPA. I had a Young Faculty Award through the BTO office a few years ago, and that really opened my eyes to the cool science that could be done, but it was with the outcome, that applied outcome or operational biotech, which is, I think, really exciting. And there's the saying that the problems that DARPA is working on are DARPA hard. Like, they're really, really difficult. And if we can get even part of the way there, it would be transformational. And that's, I think, what I really enjoy about the things we're doing. Like, it's almost a little bit crazy, but in doing it, we're able to deal with these big, big challenges. The work that we're doing takes a lot of different people to address these problems. I'm a microbiologist, and I think that bacteria are fantastic and have a lot of solutions to problems, but microbiologists on their own can only solve so many things. And so I think the thing that I really enjoy about what I'm doing as part of this program is that I get to work with all these different scientists from all these different disciplines. We're working with chemical engineers, electrical engineers, material scientists, and bioengineers. And I think there's something that's fun about being in meetings where I bring my unique expertise, but it's really the combination of all of those. And I think, I don't know, this is probably cheesy, but I think that what I like about bacteria is that it's really the strength is in the interactions and the cooperation that happen in those communities. And I think in the same way, it's these interdisciplinary teams that is really exciting and will allow us to get closer to that, addressing these problems. And I think that DARPA catalyzes a lot of that through proposing these big challenges and giving resources to pull these big teams together. So I want to acknowledge that I'm just a small part of one team, and there are a lot of other teams that are working on the resource program. But then also there's something really exciting about that combination of efforts and expertise that gets us closer to solving these big challenges.
Thanks for joining us, and thanks also to Tom Shortridge for producing this podcast. For more information on the DARPA Cornucopia and resource programs or other work at DARPA, please visit darpa.mil. There you will also find a link to download this podcast.